So, can anybody tell me what we're doing right now? What we just finished? What kind of idea? Yes, I know.
Fundamental theorem.
Fundamental theorem of calculus, right? So that gives us a way of getting the definite integral, right? Gives us a way of getting the definite integral of some function, right? So you find an antiderivative, and then you evaluate it at the endpoints. Okay. So today we're going to do section 5.5, which is called substitution. Substitution. It's there are two versions of it. One is for indefinite integrals. One is for indefinite integrals, and then the other is for definite integrals. Okay, but really, most of it is, well, okay, so there's two versions of it, and the first one is indefinite integrals. Remember, what an indefinite integral is basically just the collection of antiderivatives, right? And so this gives us a way of finding antiderivatives. Okay. Gives us a way of finding antiderivatives when it's not completely obvious in certain cases. Okay. How many of you have seen this before? Substitution, so-called u-substitution. Okay, so a lot of you have seen it. Some of you haven't seen it. That's okay. Yeah, often it's called u-substitution because one uses the variable u a lot. Okay, so let me just show you how one does it. How one does it. Okay, and we'll give an example. Okay. So you're given an indefinite integral. Somebody says, find the antiderivatives of sine cubed x cosine x. Okay? It says find a function whose derivative is this. Right? Those of you who've seen this before, don't answer the question. Okay, but those of you who haven't seen u-substitution before, how would you make a guess? Can you make a guess as to what function would be, what function would you want whose derivative would be this function? Right. You want some function, right? You're looking for some function whose derivative is this guy. Right? Yes?
Sine of x.
Sine of x. So you want a function whose derivative is sine cubed x cosine x, right? So what function, if you differentiate it, gives you sine cubed x cosine x? It's not that easy to do if you haven't seen this trick before. Tanima?
You can do it without using the trick, though.
Sure. So yeah. So how would you do it? Yeah.
It would be sine x, like sine 4x over 4.
Yeah, sine 4x over 4. So you say, well, just by sort of guesswork, maybe, just by trial and error, you'd say, well, I want to get a sine cubed here, right? I want to get a sine cubed, so I know that if I differentiate sine to the fourth, I'm going to get 4 sine cubed. By the chain rule, I'm going to get 4 sine cubed cosine x, right? So you make some guess, right? So that would be a way to do it. So you make some guess, like, well, it's got to have something to do with sine cubed, sine to the fourth. If I differentiate sine to the fourth, I get 4 sine cubed cosine x. Well, that's pretty close. I'm just off by a factor of 4. So I take my original thing, I divide by 4. And then I get the right answer. Okay, so you could do it by sort of like guessing and then fixing up your guess, right? Okay, so that's if you really understand the chain rule, then you've got some idea of how to make your guess. Okay, So this is, for u-substitution, what you do is this. You say, so here's the trick. It's not really a trick. You let u be sine of x. Okay. Then the u dx is, if you differentiate this function, you think of this thing as a function. If you differentiate it with respect to x, what do you get? You get the cosine, right? And so you rewrite this thing in terms of u. So rewrite in terms of u, and you would get well, sine cubed x, so that's u cubed, cosine x dx. Okay, and you do the following thing, which is not really legal at all, but we do it anyway. You say du is cosine x dx. Okay, so you replace this cosine x dx with du. Okay, that's completely illegal, right? Because it's not like you're dividing du by dx. When you differentiate something, right? This is really u prime, right? When you differentiate something, there's no division going on. It's not like you can multiply by dx. Okay, but it turns out that this notational trick is okay to do. Okay, but just to make it clear, this idea that the derivative is something divided by something is not right. Okay, so it's not really legal to do this, but it works out. Okay. Okay. So you say, okay, I'm going to take my u to be sine x, then du turns out to be cosine x sine x, cosine x dx, right? And so this thing, if I write it in terms of u, is u cubed du, right? If I integrate u cubed against du, what do you get? What do you get? You cubed, Hunter?
U to the fourth divided by 4.
U to the fourth divided by 4 plus constant, right? And then you switch it back, right? So now switch back to x, right? And u was sine x, so you get sine x to the fourth over 4 plus c. Okay, so this is the trick of u-substitution. Okay, so we'll talk about why we can do this in a couple minutes, but for right now, let's just do some exercises to show you how get you used to actually doing it. Okay, so right, we had to choose. Right, we had to choose something that we called u, right? And the way we chose our u was we looked at it and we said, well, is there something that we have the derivative of here, right? We said, oh, well, the sine works, and we have the derivative of sine, right? So that'll give us the du that we're looking for. Okay, we take our u to be something whose derivative is in there. Okay, okay. So here's an example. Try this one. Think of what you would choose as your u, and then evaluate it. Okay, turn to somebody nearby and tell them what you did.
Yeah, I think it was
Okay, so who would like to tell me what I should choose as my u? Except for the regulars? You count as a regular. Jake.
Natural logarithms.
Right. So you said, okay, let's let u be the natural log of x. And why did you choose that?
Because the derivative of that is 1 over x.
Yeah, because the derivative is 1 over x, and we've got this 1 over x sitting there, right? So you say, okay, so then my du is 1 over x dx, and we rewrite this thing as u du. Right? Okay, everybody okay? Right. Okay, so then you integrate that, that's u squared over 2 plus c, you switch it back, and you get natural log squared over 2 plus c. Right. Okay. And if you differentiate that, you see that that actually is an antiderivative, right? Because by the chain rule, you're going to get 2 natural log x to the 1. So the 2's will cancel out, right? You get natural log x, then times 1 over x, right? Times 1 over x, right? When you differentiate this, right, you're going to get this to the 1 times the derivative of the natural log, right? Which is natural log x over x. Okay. Another one, basically very similar. If I have natural log x square root over x dx, and I'm looking for an antiderivative of that, take a minute to do that one. Okay, turn to somebody nearby and talk to them, please.
So like, it doesn't
Okay, so somebody tell me what U I should take. This time. Natural log of x. Yes. What's your first name?
Jessica.
Jessica. I don't remember your last name. Okay. Yes. Right. And same reason, right? Because you see that the derivative is 1 over x, and we've got the derivative, right? So derivative is 1 over x. Right? So we rewrite this as u to the 1/2 du. Right? Everybody okay? Right? And so you integrate it, you get u to the 3/2 divided by 3/2 plus c. Switching back, you get 2/3 natural log to the 3/2 plus c. Right. Let's do a couple more. Let's just do this one together. X squared plus 1 to the 7 times 2x dx. What's the answer? What am I going to use as my u? Stay. X squared plus 1. So I take my u to be x squared plus 1. Du is going to be 2x dx. Right? And so I've got integral of u to the 7 du. That's just u to the 8 over 8 plus c. In other words, x squared plus 1 quantity to the 8 over 8 plus c. Okay. If I had just x dx, right, then what am I going to take as my u?
You're still going to use 2x. I mean x squared plus 1.
I'm still going to use x squared plus 1, right? And you say, okay, well now my du is 2x dx. So, you might be thrown off. I don't know, be thrown off by this. But you say, I only have x. I don't have 2x. That's okay. Just put in a 2. No, that's not right. You can't just put in a 2 whenever you feel like it, right? But you can always multiply by 1, right? So you can put in a 2, multiply by 2, and divide by 2. Okay. Right. So it's always okay to multiply by 1, and sometimes we'll throw in more clever-looking ones, and sometimes more stupid-looking ones. So this is not a particularly clever one, right? 2 divided by 2. Okay. Okay. So you get 1/2 of u to the 7 du, right? So it's 1/2 u to the 8 over 8 plus c, right? That's, I switch it back, I'm going to get u to the 8 over 16 plus c. Now, you might say, well, why didn't I multiply the c by a half, right? Why didn't I multiply the c by a half? Well, it's because the c ranges over all numbers, right? So, if I wrote this as plus c over 2, as c ranges over all numbers, it's the same thing as saying plus c as c ranges all over all numbers, right? Because c over 2, c over 2 as c ranges over all numbers will give you all numbers, right? So I may as well just call this c. Yes, Andy?
Why did you add the 1/2 again?
Why add the 1/2? Well, because I didn't have my du, right? This was the original problem, right? So I've got my du should be 2x dx. I only had x dx, right? So I want to have du there. Right? So I say, okay, there it is. Okay, but you can't just multiply by 2. You can't just take your function and multiply by 2 because you feel like it, right? So I'm going to also divide by 2, right? So I multiplied by 2 and I divided by 2. I multiplied the thing by 1. That's okay, right? It's okay to multiply by 1. Yes, Hannah?
Can you simply just divide du by 2?
Sure. Yeah, so you could say, okay, I know that 1/2 du is x dx. Right? You could do that as well. So instead of multiplying this by 2 and dividing by 2, you would say, well, this is u to the 7th, u to the 7th, and then x dx is 1/2 du. Right? 1/2 du, and I get the same thing. I get 1/2, u to the 8 over 8 plus the constant. Either way, that's fine. Okay. Any questions? Okay. So, what's really going on here? let's remember the chain rule. Okay, let's remember the chain rule. Okay, so if I have the derivative of g composed with f, right? What does the chain rule say? That the derivative of a composition is going to be what? Hunter?
G prime of x times f prime x.
Right. G prime f of x times f of x. And let me call this g prime little g. Okay. Let me just say, just by notation, let little g be the derivative of big G. Okay. Okay. So that's the chain rule. Now, if I write that backwards, that's the same thing as saying that the integral of g of f of x, f prime x dx, right? This is saying that this is an antiderivative of that. In other words, the antiderivatives of this are g of f of x plus some constant. Right? So the chain rule, if you write it written using indefinite integrals, right? This is what the chain rule says, right? That the derivative of this is this. Okay? I just wrote the chain rule twice, right? Everybody see that? I wrote the same thing twice, right? The derivative of this is this. In other words, the antiderivative of this is this, right? The antiderivative of this is this. Okay, so I just wrote the chain rule twice. Okay. So, okay, so, well, if we write the integral of if we write this as the integral of g of u du, right, we let u be f of x. If we write this as the antiderivative of little g, well, what's the antiderivative of little g? It's just big G, right? This is big G of u plus c. In other words, big G of f of x plus c. So u-substitution is just a sort of shorthand for making the it's just a shorthand for this. Okay, right? Like, let me see if I can say it more clearly. I'll say it again. The antiderivative of this is this, right? By the chain rule, right? Okay, so if somebody gives you this thing here, and you do this u-substitution, you see what you get. You're going to get this thing, which is the right answer. Okay, so it's just that doing the u-substitution allows you to get to the actual antiderivative. It's a sort of a shortcut of saying the actual antiderivative. Okay. I guess what you want to get out of this is that what u-substitution is just the chain rule in reverse. Okay. U-substitution is just a chain rule in reverse. Okay. Basically, the laws of integration that we're going to see. So right now we're going to do some tricks of integration. Several of them will just be tricks of differentiation in reverse. Okay, so the chain rule in reverse is u-substitution. The next thing we're going to see, integration by parts, is just the product rule in reverse. Okay. So everything, the laws of integration will correspond to laws of differentiation that you've seen before. Yeah, Tiffany.
So if you asked us to prove the u-substitution, we would have to prove it by saying this is the chain rule, and if we used u-substitution, it would.
Yeah, basically. Yeah, you say, well, look, the chain rule tells you that this is true. And if you do u-substitution, that gets you to the actual answer. So that's why u-substitution works, basically. Okay. So that's all I want to say about the indefinite integrals, right? So you can use the u-substitution to get antiderivatives, but you can also use it to evaluate definite integrals. So evaluate using substitution to evaluate definite integrals. So again, let me start off with an example. Okay, so somebody asked you to integrate t squared minus t to the fifth times 2t minus 1 dt between 1 and 2, from points 1 to 2. Okay, so we'll give you two ways of doing this. Okay, first is use the previous method to find an antiderivative. Then use fundamental theorem of calculus 2 to evaluate. Okay, so take 10 seconds and write down an antiderivative of this. Use the u-substitution to figure out an antiderivative of this. Okay, you can tell me. Proceed.
By taking t squared minus t as u, then you get t squared minus t over 5.
So you get u to the fifth times,
That's the
that'll be du. U to the fifth du. If you integrate u to the fifth, you get u to the 6 over 6, right? So the antiderivative, the antiderivative would be u to the 6 over 6 plus c, right? And then you use the fundamental theorem of calculus 2, and you evaluate that thing between 1 and 2, right? And so you get 2 to the 6 over 6 minus 0 over 6. Okay, so you get 2 to the 6 over 6. Okay, so that's one. That would be we're basically using the first method to evaluate definite integrals. Okay, everybody okay with that? Questions? No? Okay, so that's one way. There's a shorter way, which is, so method 2, use u-substitution to use u-substitution and adjust the range of integration. Okay. So you take your thing, 1, 2, t squared minus t to the 5th, 2t minus 1 dt, right? And you say, okay, I'm gonna switch my variable. I'm gonna let u be my new variable, right? Where u is t squared minus t. Okay, this is what's called a change of variables. I mean, they're both called change of variables. Change of variables. Okay, my du is 2t minus 1 dt, right? And so I rewrite the thing as u to the 5th du, but I have to adjust my range of integration. So originally, I'm integrating over t, right, as t goes from 1 to 2, right? I've got some function, t goes from 1 to 2, right, whatever my function is, right? But now I'm switching to a new variable, the u variable, okay? And, you know, I've got a different function. It's just u to the 5th, right? U to the 5th, whatever that looks like. Something like that. Okay. And I have to adjust my range of integration. The way you do it, you say, well, when t is 1, u is going to be 0, right? Right? U is really a function of t, secretly. Right? U is really a function of t, depends on t, right? When u is 1, I'm sorry, when t is 1, u is 0, right? So, 0, right? When t is 1, 0, right? When t is 2, I get 2. Right? Because you get 2 squared minus 2. That's 2. Okay? And so I get u to the 6 over 6 between 0 and 2. Okay? And that's going to be 2 to the 6 over 6 minus 0 to the 6 over 6. Okay? And you see that as long as you evaluate the new integral with the proper bounds, you get the correct answer. Now, if I use the other bounds, you don't get the right answer. Right. Okay. So one way, first way is to find the antiderivative using the u-substitution, and then switch back to the original variable and evaluate between these bounds. Or you go all the way and switch over into the other variable completely and say, okay, I've got this new variable and I'm integrating that guy between these new bounds, 0 and 2. Yes, sir?
Is there a preferred time to use one or the other?
Not really. Not really.
So whichever, like, you feel more comfortable with it?
Yeah, basically. Unless I say, yeah, please do it this way,
Okay.
because you should be able to do it.
Yeah.
You should be able to do it both ways. And you'll see more advanced versions of this in Calc 3, where you don't want to switch back. You definitely do want to switch completely into the new variables. Okay. Okay, so let's do some exercises. 0, 1, e to the x, 1 plus e to the x, quantity squared dx. Okay, turn to somebody nearby, talk with them, please. Okay, so what do you choose as your u? What do you choose as your u? 1 plus e to the x, right? 1 plus e to the x, right? du is just going to be e to the x dx, right? And so this thing turns into, right, we've got e to the x dx, that's my du, and then I've got 1 over u squared, right? So I've got u to the negative 2, right? Everybody okay? Right? I've got my u to the negative 2, right? Got my u to the negative 2 here, and I've got a du here. Right? Okay. And then you change your range of integration, right? So when x is 0, u is, when x is 0, then u is going to be 2, right? When x is 1, then u is going to be 1 plus e. Right? Okay. And then you integrate this thing, you get u to the negative 1 over negative 1, right? You evaluate it between 2 and 1 plus e, right? And you get negative 1 over 1 plus e plus 1 over 2.
I didn't get the upper bound 1 plus e.
You just ask, what is u? What is u when x is 0? What is u when x is 1? Right? X is going from 0 to 1. That means that u is going from u of 0 to u of 1. Right? Well, u of 0 is 2 and u of 1 is 1 plus e to the 1. Okay. Okay. One more. Let's do this one together, say. 0, pi over 4, secant squared tangent. I'm sorry, secant cubed tangent. Okay. Well, actually, let me let you have 1 minute to think about what you would choose for your u. You have a question, Hannah? Yes, what's the question?
For negative u to the negative 1, do you not divide by 2?
No, right, because I've got u to some power, right? The antiderivative of that is going to be u to the power plus 1 over the power plus 1. Okay, turn to somebody nearby and say, my u is... Okay, what should we let u be? What should u be? What should u be?
Secant squared.
Secant squared? Are there suggestions? Tangent?
Secant tangent.
What's the derivative of secant squared? What's the derivative of secant squared? Well, it's going to be 2 secant times the derivative of the secant. What's the derivative of the secant? What's the derivative of secant? Secant times tangent, right? So secant times tangent. Okay. So not quite, right? Because if this was secant to the fourth, that would be great, right? Because then we would have u and we'd have du right there, but we don't. Okay. Now, what about tangent? What about tangent?
Secant squared.
Yeah, secant squared. Okay, but then we've got u, or we've got du, and we've got a leftover secant, right? So anybody think of one more possibility? Yes?
Secant.
Secant. Yeah, secant is actually the one we use, probably. Okay, so let's use secant. Right. Then du is secant tangent. Right, and this thing becomes u squared du. Right, secant squared times secant tangent. Right, secant squared times secant tangent, which gives us our secant cubed. Yes, Catherine?
Do you expect us to memorize all of the different integrals and ranges?
All the what? Like-
say for secant is secant x tan x and stuff.
Yeah, that's stuff you should know. Yeah, that's stuff you should definitely know. And then, right, you say, okay, well, when t is 0, you get, the secant of 0, which is 1. And then on the other end, you get the square root of 2. And so you evaluate it, u cubed over 3 between 1 and 2. You get root 2 cubed minus 1 quantity equals 3. Yeah.
How did you get blue squared?
Because this thing I'm going to rewrite as secant squared secant tangent. Right, I'm going to break my secant cubed into secant squared secant tangent. Right, so I get u squared du. Right, secant squared becomes the u. Right, you're the one who chose u as your secant, right? So we get secant squared, and then we get du. Okay.
We were expected to know like what pi over 4 is when you plug it into 10 and stuff like that.
Say it again?
Also. And we're supposed to know like where pi over 4 lies on the graph if you plug it into 10 or like see.
You mean like, should you know what the secant of 0 is and the secant of pi over 4 and stuff like that? You should probably be able to figure it out. So let me say, yeah, you should. Now that's not to say that I'm going to ask something like that on the exam, but you probably should know it. Okay. Okay. Let me just take a couple seconds to say something about why we changed the range of integration. Okay. Why we change the range of integration. Well, it's because if we're integrating, let's go back to our previous notation, right? If we're integrating this thing, so again, g prime is little g. If we're integrating something like this, right, well, that's going to be big G evaluated between A and B. Big G of f of x between A and B. Right? That's big G of f of B minus big G of f of A. Right? So, right, that's the same thing as the integral of little g of u du between what and what? F of A and f of B. Right? We need to integrate this guy between f of A and f of B, not between A and B. Right? So that's why when you switch to the u variables, you have to adjust the, right? So u is f of x here, right? When you switch to the u variables, you have to adjust the range of integration. Right? You don't go between A and B, you go between f of A and f of B. Okay. Okay, that's it for today.